Okay, in this video, I'm going to go through Edexcel AS Chemistry, paper 2, which is the 2018 paper, and I'm going to do the second half of this paper. I've done the first half in an earlier video. Okay, question 6 then. The question is about the synthesis and reactions of butane 1,4-diol. Okay, butane 1,4-diol can be synthesized from butene 1,4-diol by the reaction with the reagent B. Identify reagent B and give conditions. Okay, so all that's happened there is we have added hydrogens across this double bond, made it saturated, and so if you remember, the reagents for that are hydrogen with a nickel catalyst. Right, then it says what is the reaction is best described as. I was thinking addition reaction, but this isn't down as an option, and so reduction is definitely the best one there. You're adding hydrogen. In organic chemistry, when you add hydrogen, it's the same thing as reduction. Right, it's certainly not oxidation or any of the other options there. One of the commercially important products can be manufactured by this type of reaction with an alkene group. Well, this is to make saturated fats. So you get unsaturated fats, react them with hydrogen with the nickel catalyst, and it makes them saturated. And of course, that makes them unhealthy, and that's increasingly less these days because it recognized as being pretty unhealthy. Right. Butane 1,4-diol can be oxidized to form butane dioic acid. Okay, so butane dioic acid is a solid at room temperature. Right, describe how you'd make a 250 centimeter cube solution of the acid. And you want to know the concentration accurately, but it's got to be about 0.05 mol per dm cubed. And it says it's sufficiently soluble in water to achieve that. And they also give you the MR. Okay, right. So this is a bit of a calculation and also how to make a base standard solution, which is pretty important. Right, so let's do the calculation first of all. How many moles of butane dioic acid do we need? So moles is going to be equal to concentration times the volume. Well, the concentration we want is 0.05, and the volume 250 centimeters cubed, so that's 250 over 1,000 dm cubed, that's 0.25. So that is equal to 0.0125 moles. That's how much we need. Now, what is the mass that we need there? So we're going to use mass is equal to moles multiplied by MR. Okay, so the moles is equal to 0.0125, and the MR butane dioic acid is 118. All right, so that mass we would require would work out to be 1.475 grams. Okay, now how are we going to? So we need around about that much mass. Now, so how are we going to do that? Well, first of all, you're going to get a weigh bottle, and you're going to put in there somewhere in between, let's say 1.35 grams and 1.55 grams, around about this value here of butane dioic acid. Right, and you want a balance either to 3 decimal points or 2 decimal points. So what you're going to do is you're going to weigh the amount of butane dioic acid by subtraction. So weigh the bottle, then add the solid to a 250 beaker, 250 centimeter cube beaker, and reweigh the bottle. Then you're going to record the mass used by subtraction, or calculate the mass used, the mass transferred, Okay, so now you've got your solid in a beaker. I'll just draw a little diagram here. This is a 250 beaker, so you want to add about 150 centimeters cubed of distilled water to that. Stir it and dissolve it. Okay, then you're going to transfer that into a volumetric flask. And I would definitely in your answer use the word volumetric flask. Don't say a flask or whatever. It's got to be that. Volumetric flask of 250 centimeters cubed. So add the solution. Now obviously you're going to have little bits of solution left in the beaker, so then you're going to rinse the beaker and the stirring rod and add the rinsings to the flask. You probably want to do that ×2. Then you're going to make up that with distilled water to the mark. With distilled water. And then very importantly, it's important to say stop of the flask and invert several times to make sure it's mixed up. If you don't do that, you tend to just end up with distilled water in that part of the flask and a more concentrated solution at the bottom. So that is all you need to say. For 6 marks, that's the entire procedure. Okay, right. So here's a titration of a weak acid with a strong base. So ethane dioic acid this time. So it's all right. A weak diprotic acid, so it's going to react in a 2-to-1 ratio with NaOH. Okay, diprotic means it's got 2 H pluses to give away. It's going to be used to determine the concentration of sodium hydroxide solution. So 25 centimeters cubed of the solution is placed into a conical flask. And then you're going to titrate that against sodium hydroxide solution. So the NaOH is going to go in there. And the purpose of this is to find out the concentration of the sodium hydroxide. Right, so let's go through this. Here's the titration results. All right, now we've got to say which ones are concordant. Okay, which one should we use? Tick the titer, this one here. Tick the titer values that should be used to find out the mean. And okay, so which are concordant? They've got to be within 0.1 centimeters cubed of each other. So this one and this one and this one should all be used. That one is outside, not concordant. So the average of those three, add them together, divided by 3 is obviously going to be 17. Put it in the box. 17.70 centimeters cubed. And we're going to need that later on. Okay. The equation for the reaction of ethane dioic acid with sodium hydroxide is this. Okay, so it's reacting in a 1:2 ratio. Calculate the concentration of the sodium hydroxide solution. Okay, so let's do that. Right. So it tells us our ethane dioic acid solution that we've got in there. Right, this one is 3.8 grams per decimeter cubed. That's the concentration. Okay, so let's work out how many moles we've got in a decimeter cubed. We've got that many grams in a decimeter cubed. So let's write down the moles in 1 dm cubed is equal to the mass over the mR. So that's going to be 3.8 over the mR is 90. So that is equal to 0.04 22, and that's moles. So therefore the concentration of our ethane dioic acid solution is going to be, well, we've got that many moles in a dm cubed, so it's 0.0422 mole per dm cubed. Now we need to work out how many moles we've got in the flask. Okay, now we added that volume, 25 centimeters cubed of this solution. So let's write that down. Moles acid in 25 is equal to the conc times the volume. The concentration 0.0422, and the volume is 25 over 1,000 in dm cubed. And that gives us 1.055 times 10 to the minus 3 moles of acid. Okay, so how many moles of sodium hydroxide have we added to that in the from the burette? Well, it's a 1:2 ratio here, so that we've with the moles of NaOH is going to be double that. So moles NaOH in the titer of 17.700 centimeters cubed, that's going to be 2 times 1.55 times 10 to the minus 3. That is equal to 2.11 times 10 to the minus 3 moles. Now we need to work out the concentration of NaOH, so we do moles over volume. Okay, so concentration, moles over vol. The moles are 2.11 times 10 to the minus 3. The volume is 17.70 centimeters cubed. That was our titer. So that's 17.7 over 1,000. That works out to be 0.1196 moles per decimeter cubed. Now, I think the question asks us to give it to, or it tells us it wants it to 3 significant figures. So we should round that up, and that should be 0.112 moles per decimeter cubed. That's our final answer. Okay, ethane dioic acid is a weak acid. Name a suitable indicator for this titration and state the color change. Right, you can't use methyl. The 2 indicators you used are usually methyl orange or phenolphthalein. Yeah. Right, now methyl orange can't be used with weak acids. And so you must use phenolphthalein here. Incidentally, phenolphthalein can't be used with weak alkalis. Now, what's the end point? Well, phenolphthalein, this is colorless in acid or neutral solutions, and it's pink in alkali solutions. Right, so here we are adding the NaOH into the conical flask. So the color change, the endpoint, you want from colorless to pale pink. So we're doing that the other way around. Normally you end up with you put the NaOH in the conical flask, and so the endpoint would be colorless, but in this case the NaOH is being added from the burette. Okay, now on about percentage uncertainty and stuff. Right, the uncertainty in each burette reading is plus or minus 0.05. Okay, calculate the percentage uncertainty for titer 4 and for the pipette volume. Right, here's titration 4. I just posted that in there. Okay, so the percentage uncertainty for the burette. Right, you do 2 burette readings, start and finish, so you've got to double that. So that's 0.1 over the total volume, which is 17.65. times 100, that gives a percentage of 0.57%. Right, now let's do the pipette. The pipette, you remember in the question it said was used to transfer 25 centimeters cubed. And the uncertainty for the pipette, they tell us, is 0.06. So that's 0.06 over 25 times 100. That will give 0.24% for the pipette. Okay, there are the two uncertainties there. Right, which of the following changes would halve the percentage uncertainty? Right, so in the volume of liquid measured by the burette. Now we want to halve the uncertainty. What we've got to do is we need to double that volume. We need to double the volume of NaOH. So we can do that by either making the NaOH more dilute, or we could do it by make the acid more concentrated. So let's see which alternatives are there. Make the acid twice as concentrated. You need twice the volume of NaOH. Halve the acid concentration. No, that's wrong. Double the acid concentration and leave the volume. That would work. So yeah, use 25 centimeters cubed of acid, but double its concentration. That would work. Double the acid concentration, halve the volume. That would mean you have the same titer. So halve the acid concentration. That would mean you use only half the titer, so you'd increase the error. So B is the answer there. Okay, question 8 onto organic chemistry. Okay, draw the displayed formula of 2-methyl-propan-2-ol. So let's draw that. So there's the skeleton. We've got a methyl there. We can have an OH. Now, because it's displayed, you can't write OH. You've got to write O and a bond and H. Yeah. So there's our displayed formula. Okay, now that's just about mass spectrum. The relative molecular mass of this stuff is 74, but you don't get a peak at 74. There's no peak at 74. Give a possible reason and why there is no molecular ion peak. Why there's no molecular ion peak in the spectrum. Right, it must be that the molecular ion, which would be C4H10O plus, that must be unstable. It must fragment into something else, and so none of it reaches the detector. So that would be the answer to that one. Now it's going to probably ask us what is the likely identity of that big peak we're seeing there at 59. Yeah, I think it does. Write a formula of the species that could be responsible for the big peak at 59. Right. So there's obviously some kind of fragmentation. The whole thing weighs 72. Well, let's have a look here. If you right, let's say if a methyl drops off that weighs 15. So 72 minus 15, that's is 57. So it's not that. Okay, it's not that. So it can't be. It's not. This is not the fragment, because that would weigh 57, and ours is at 59. So let's get rid of that. Actually, that would be 59. Sorry, yeah. You get rid of that 15. Yeah. So you lose that, and this thing would weigh 59. Thing in green. So and the identity of the peak is get rid of that one of those methyl groups, and that positive charge on that. Okay, so that is the likely fragment. That's giving you 59. The equation for the complete combustion of 2-methyl propanol is given below. Use the bond enthalpies shown to calculate a value for the enthalpy change for the complete combustion. So we want to find out delta H for that. That's the complete combustion using bond energies. So I've drawn it out here already. Okay, so we've got our 2-methyl propan 2-ol, and we've got 6 oxygens, and we've got the combustion products here. We've got CO2 and water. So when you're given bond enthalpies, what I like to do is to write down, so the gaseous atoms at the bottom here. And what we're going to do is we're going to break all of the bonds there, and then we're going to make the bonds there. So let's see, which bonds are we breaking on the red arrow? And now remember that breaking bonds is endothermic, so they're going to be positive values. Right, we're going to break 3 times carbon-carbons. So that's 3 times 3, 4, 7. We've got to break, in blue, we've got to break 9 CHs. That's 9 times 413. We've got to break 1 CO. And that's 358. And we've got to break 1 OH. And that's 464. And then finally, we have got 6 of the oxygen-oxygen double bonds. And they are 498 each. Add up that lot together, that will give us 8,568 kilojoules, okay? And that's going to be plus because we're breaking those bonds. Now on the green arrow on the right hand side, we are going to be making bonds. So these are all going to be negative values. So we're going to make, we're going to make 8 carbon oxygens. So that is 8 times minus 805. And we're going to make 10 of these oxygen hydrogens. So that's 10 times minus 464. Add all that up together, we get minus 11,080. Right, now delta H is going to be equal to, right, it's going to be plus 8568 on the left hand side, plus this negative number minus 11080, and that gives us a final answer of minus 2,512 kilojoules per mole. That's delta HC, the enthalpy of combustion. Okay, it's pretty straightforward, but a lot of opportunity for making sort of careless errors there and getting the wrong answer. So important to show you working out. Right. 2-methyl propan 2-ol burns in air with a smoky flame. Explain how burning with a smoky flame affects the experimentally determined enthalpy of combustion. Well, a smoky flame means that you're getting incomplete combustion. Because you are making, so you're not getting CO2, you're getting some solid carbon. That means you'll get less energy out than expected. So delta HC will be less negative. Rather than say not as big, it's probably better to say less negative. Okay, right. A data book value for the enthalpy of combustion of 2-methyl propan 2-ol was this here. Gives the main reason between our value, which was, what was it? We got minus 2,512, which is quite a bit smaller than that. The main reason isn't really the incomplete combustion. You probably realize it's probably due because heat loss to the environment, rather than going into the water in the calorimeter, it's just going into the air. Heat loss to the environment. Okay, which observation would be expected when 2-methylpropane-2-ol is in heat with potassium dichromate? Well, just to draw the structure out again, it's like this. We can see, well, what kind of an alcohol is that? It is a tertiary alcohol. That means you can't oxidize it, so there will be no oxidation. So that means that the dichromate will remain orange. So it will remain orange. Dichromate, remember, if it does oxidize something, it gets reduced itself to the green chromium, orange to green. That only happens with primary and secondary alcohols, not tertiary. And that is the end of the questions there.